Yes, so this is not the typical time of day that I'm used to talk, but I think I will groove into it in the next couple of slides. I'm going to present an overview about a environmental seismology project that we completed the data acquisition for pretty much a year ago in February 25 on Lake Pääjärvi in southern Finland. And the project, it's called DYNALake. It's a Research Council of Finland supported research project, but it also is received support from FAME, so it's a perfect venue to introduce what the project is about and show some first results. So the motivation is to resolve micro and macro scale properties of seasonal lake ice that is shaped by environmental processes. On the left-hand side, you see what I refer to as micro properties. So you see sketches in the center. You see an illustration of a lake sediment where organic processes are responsible, for example, for methane production. In these methane bubbles rise in the water column and they integrate in the ice while it's forming together with other trapped air from the atmosphere. And you see that from the picture to the left. So this is a photograph of ice from Lake Pääjärvi from last year, where you see all these bubbles that contain different kinds of geochemical traces. And on the right-hand side, you see what I refer to as macro scale. That's an aerial view taken from a drone. You see for scale people zipping around with scooters or ATVs, and you see these 10 meter, 50 meter scale variations, shades of gray that also refer to like larger scale spatial variation of ice properties. And the project is about having an experiment that allows us to image and monitor the lake ice dynamics and to provide some base or ground truth observations for developing seismic methods to be able to infer environmental processes efficiently. So just a short overview about the environment. So again, like I said, the lake is situated some 100 kilometers north of Helsinki. It's conveniently located next to the Lammi Biological Station of the University of Helsinki, or of course the other way around. You see the bathymetry of the lake and this red zone in the center. So I hope you see the mouse zipping here. That is a rift that we found, and this is an aerial view of that rift. This is maybe a meter wide. And on the right-hand side here, we see a zoom in of temperature profiles. So it was a bit in peril to do this experiment last year because the temperatures were kind of mild in December, but then we had a drop here to minus 10-ish in the 2 weeks before, and so we could set out and actually move along with this deployment. This is a header or like a head start to what you have to think about of seismic or elastic wave propagation in the ice. So this sketch here in the upper left, they illustrate a thin ice sheet or plate if you want. So on the radial component, there is an undispersive wave called QS0 that has the deformation pattern that looks like this. Not shown is a shear horizontally polarized mode referred to as SH0 that is also not dispersive, and then we have these flexural modes that are highly dispersive and they are referred to as QS. And if we look at a spectrogram of waves like this, we see here again this highly dispersive slow QS node and this SH0 and QS0 waves that have linear move out here. And on the upper right we see waves propagating between the many sensors that I'm going to talk about on the lake. So you see that the RRTT, these quasi-symmetric waves, they propagate over a distance of 10 kilometers, whereas on the right-hand side you see that these flexural waves, they dissipate because of their dispersive nature much faster. So that's a busy slide, but that's the centerpiece of the experiment. You see the lake outline. Each red dot is a geophone that we installed. So we installed 300 in total geophones on the lake. On the lake itself, it follows this neat mathematical pattern. These shapes are called specters. So this is a kind of new development. And the reason that we do is because it has some optimal properties in terms of resolution and ray coverage if we want to do tomography later on. We also deployed some circular arrays that allow us to do beamforming. In the center area here, we have a rotational sensor, like some broadband sensors, accelerometers. In the upper left, you see a fiber optic cable. So this is what you see here on the left. So this is a very thin cable that is coupled to what we call interrogator, and it measures strain along the cable. But this can also be interpreted as capturing the full wave field at super high spatial resolution. So you can tinker with it and you can have a spatial resolution like a gauge length of only 10 centimeters. So we have a 1 kilometer cable and sample the wave field, for example, every 10 centimeters. And we have also a microphone installed in order to listen to these sounds that ice quakes make. And from this data analysis, we can also infer something about the lake ice properties. So this is what we did in a week about a year ago. So we went there and plastered the full lake with these sensors. In addition, we had a geochemical probing and hydroacoustic sounding. So each of these diamonds represents the location of sediment coring or lake ice geochemical analysis, in order to get an idea again about what are the environmental processes, especially when we think about ebullition of potential methane from the lake. So this was measured in situ to have ground truth or observations that we can relate to our seismic interpretation later on. And we also have these 3 axes here where people, collaborators from Stockholm, hung this echo sounder into the water column. So this is a sketch of what's happening. So it's pinging like an echo sounder does, and the reflections of it should hopefully indicate rising methane bubbles or fish. So we can see some traces here. So these are move-off patterns of bubbles, and we can think about that there can be fish. But further analysis also pending whether we found some hotspots of methane ebullition, but that would be a long shot to just find spots or places where it's actually happening. Here we see measurements of the ice thickness. So the top 2 images show ice thickness measurements in this period range, and then at the end of the deployment, you see that it has thickened. So at each place where we developed or where we deployed a geophone on the ice, we took depth measurements or of the ice sheet, again also for ground truth measurements, and they are in the range of 20-ish to 30-ish centimeters. So it was quite decent. If you would do it today, like after these 2, 3 or even 4 weeks of very cold weather now, it would be I guess towards the 50 centimeter range. But it was sufficient to walk and to maneuver on the ice safely. And you see here that in the shallower and more narrow portions, the ice is thicker than in the central part, but the central part has a larger growth rate over the experiment. Now here I show you an ice wave example. So this is another map that shows hammer shot. So a colleague, Felix Strobel, he's a PhD student. So we left him after we deployed the instruments for maintenance, and he went there and did a couple of hammer shots. These are indicated by the blue dots. And on the top here you see what these flexural waves look like. So they are highly dispersive, as you can see. High frequencies arrive early before low frequencies, and this is totally different from what we typically see as seismologists for Rayleigh waves that are also dispersive, which should be the other way around. So it has a distinct signature. And here in the bottom left we see a spectrogram of that. So this curved feature here, so this is frequency over time of this geophone record here, shows this highly dispersive wave that was indicated or excited by a hammer shot, and the dispersive nature can help us to infer later the thickness or the elasticity of the ice. This is an example from microphone recording. So the microphone is installed here at the upper left of the lake at the end of that cable. This is this diamond here, and on the left hand side we see a microphone recording, and on the right hand side we see ice quake recording on the vertical, radial and transverse component. We see here again the QS not arrival on the vertical and radial component, the somewhat slower SH not arrival. So in terms of seismology, they are related to P and S waves. And then again, this highly dispersive QS wave that looks similar. So the dispersive nature here on the microphone looks similar, but then it reaches a coincidental frequency that is related to some coupling phenomena of the ice, and it can help us to infer the thickness, but also the duration and thickness and direction towards the source. This is a short example of what the signals look like in that cable. So here is a stack of low frequency waves that propagate along that cable in the upper left of the lake, and these are dispersion curves inferred from these signals. And on the right hand side I show results of a grid search along these four segments of the cable, and the story is that there was like wind acting over days over the open parts of the lake, and they excited a super low frequency wave that is sensitive to the ice thickness itself, but also to the water column because it's so low frequency. And that is what is captured by the cable, and also using established analytical methods, this grid search allows us to constrain the ice thickness, but also the water column. Here, this is bathymetry in the upper right along that cable, and to our knowledge, that has been accomplished the first time, and it's a quite interesting observation of what you can do with these fiber optic cable data. That's a short overview of a ground penetrating radar result. So somebody just took a radar and towed it behind a sleigh. So here the time is nanoseconds. So this is electromagnetic waves bouncing through the ice, being reflected. And this also allows us to infer the thickness and the roughness at the base layer of the ice, and to be interpreted together with the other observations that we have. I should tell that we have been making a documentary. So we're now receiving a 15-minute documentary that I think Mikko will also be keen on distributing to the FAME community. So we did some storytelling, and it's for outreach properties. We had a professional documentarist, filmmaker from France joining us. And I think we're quite happy to see what comes out of that and what the community here will see, so that not only this community can see what we have been doing in terms of this experiment. And I leave you with this output overview. So one of the major accomplishments is, of course, this data set, this environmental seismic data set, the 15-minute documentary, and then there are a couple of papers and conference presentations in the pipeline. And I hope you enjoyed this overview, and maybe there's time for one quick question or two. Thank you.